Now that we have defined the commutative property, we will look at examples that are not commutative. So, often with definitions, when you define something, you both want to define what the definition means and what it means if the definition is not true as well. So now I'm going to also define what it means to be not commutative. So recall from before, the commutative property was defined as an operation is commutative on a set means for every A, B in the set, A star B equals B star A. Once we know what the definition is, we can do the negation. We can define what it means to be not commutative. And to do that, we say star is not commutative on S. Now, the trick in this definition is we have to negate the definition of commutative. So we need to negate the quantified sentence for every A, B that are members of S, A star B equals B star A. So we need to remember our rules from foundations for the negation. When you negate a for all statement, the quantifier becomes there exists. So we have there exists in A, B in the set S, and then you negate the predicate. So here we had A star B equals B star A. The negation becomes A star B is not equal to B star A. Now, the good news is you only have to memorize the definition of commutative. You don't have to memorize the definition of not commutative if you remember your foundations well and remember how to negate quantified statements. But just for the sake of review, because for many foundations was online and for many foundations was a long time ago, let's think about this for a second. If you negate the statement, every dog goes to heaven, think about what that would mean if it wasn't true. It would mean there exists at least one dog who didn't go to heaven. If you wanted to negate the sentence, every abstract algebra student cries, which I think is a true statement, the negation would be, it would be false, so the negation would be when there exists at least one abstract algebra student who doesn't cry. So the way you negate a for all x p statement is there exists an x such that not p is true. So here, the way you negate for all a, b, and s, a star b equals b star a is there exists an a, b, and s such that a star b does not equal b star a. You change the for all to a there exists, and you negate the predicate. Now, let's see. We said addition and multiplication were commutative on the reals. Now, let's look at subtraction. I claim subtraction is not commutative on the reals. Now, to prove this first, let me write down what I want to show. I'm going to use the abbreviation WTS for want to show. So, I need to take the definition of not commutative. I need to apply it to the set being the reals and the operation star being subtraction. So I want to show that there exists, to prove this, I want to show that there exists elements A, B in the set of reals such that A minus B does not equal B minus A. Now, the nice thing is we're asking to show something exists. So the easiest way to show something exists is to just find it. I'm being asked to find two integers, or two real numbers, A and B, such that A minus B does not equal B minus A. So because I'm only asked to prove that this is sometimes not true, that there exists one pair of integers for which this is not true, I can choose the pair to be anything that works. So I am going to choose A to be 1 and B to be 2. Consider the following calculations. Now, to show that A star B does, or A minus B does not equal B minus A, I just need to calculate A minus B and B minus A separately and show that I get different things. So A minus B equals 1 minus 2, which is negative 1. And B minus A equals 2 minus 1, which is 1. And you see they don't equal to each other. So therefore, having shown, therefore, since negative 1 does not equal 1, we may conclude that A minus B does not equal B minus A. And then a black square to end the proof. Okay. We will page break that to put this all on the same page. Subtraction is not commutative on R. We want to show there exists A, B, and R such that A minus B does not equal B minus A. So we choose both A equals 1 and B equals 2. Consider the following calculations. We calculate A minus B, which is 1 minus 2 is negative 1. B minus A, which is 2 minus 1 equals 1. And since those two aren't equal, we know that A minus B does not equal B minus A. Now, here is an important thing to know about proofs with quantifiers. We said earlier we cannot prove an operation is commutative simply by looking at an example. However, we could prove an operation is not commutative just by taking a counterexample. And what we essentially did in this proof was we chose A equals 1 and B equals 2 to be a counterexample. Now, you cannot prove a for all statement true by a single example, but you can prove it false by a single example, because when you negate a for all statement, it becomes a there exists statement. And to prove a there exists statement, you only need to show it exists once, a single example to show it exists. That is why you can prove something not by taking examples, but you can disprove it by a single counterexample. Also, you couldn't prove subtraction is commutative by an example, because if you picked A and B were both equal to 0, A minus B would equal B minus A. But that being true in that one example does not mean subtraction is always commutative. So in other words, remember, when you have a for all quantifier, you can't prove it by example. But when you have a there exists quantifier that you're trying to prove, you can prove it by choosing an example. Okay, that's enough with the commutative property. We'll go to our next property.